Swayam Prabha. Digital India. Educated India.
Hello everyone. In our last session, we have tried to understand the UV protective finishes. So, in that the core mechanisms we discussed that there are three mechanisms. So, absorption of harmful radiation, reflection of incident light and scattering of UV wavelength. This we have discussed in detail, and this is basically this type of UV finishes covers the whole range of UVA and UVB, which actually comes into our atmosphere, and its photostability under prolonged exposure that we have discussed, and durability through wash cycle. So, these details we have discussed, and also the compatibility, how we can make it compatible with the textile substrates, so that the finish remains little bit permanent. Now, let us discuss the classification of UV absorbers. There are different types of UV absorbers available. First is the organic UV absorber. So, which are basically carbon based molecular structures which absorb UV photons through pi electron conjugation. So, carbon based molecular structures are used as UV absorber. So, which includes benzophenol, benzophenols, okay, and benzotriazoles, cinnamates, okay, and salicylates. So, these are the different types of absorbers, and it often offers excellent UV absorbance capability in under UVA and UVB coverage with minimal fabric discoloration. So, fabric discoloration does not take place here. If at all it is there, it is a very minimum discoloration even after the absorption of UV ray. Next is the inorganic absorbers like metal oxides, semiconductors like TiO2, ZnO2 that reflect and scatter the UV radiation. So, organic absorbers, they absorb the UV ray, okay, and inorganic, this oxides, metal oxides are used to reflect or scatter the UV radiation, and which provides a broad spectrum of protection including UVA and UVB, and it is superior photostability is there. So, as the rays are getting reflected, okay, so that they are basically superior photostable, and the nanoparticles formulation minimize the fabric whitening effect. So, that is their nanoparticles TiO2 and ZnO2 nanoparticles are used, and hybrid system, hybrid chemicals that is organic and inorganic absorbers are used to enhance the protection. So, one can combine at different proportion, that is organic absorber and inorganic absorber, to enhance the UV protection. So, sol gel matrices are used or nano encapsulation technology, which actually enhance the durability and optimize dispersion. So, this through nanotechnology and through nano encapsulation, these hybrid systems like organic and inorganic absorbers can be applied in wide variety of textile substrate. So, this technology, hybrid system technology, that we can use for very wide applications. We can get the advantage of inorganic absorber, organic absorbers, and through nano encapsulations we can get the durability. So, let us understand the organic absorbers molecular architecture. Benzophenons is one of the very commonly used organic absorber. So, organic UVA absorbers, it is aromatic ketones with strong UVA absorption. So, UVA absorption is mainly due to aromatic ketones within the range of 320 to 380 nanometer the wavelength, and the mechanism involves excited state photon transfer, and common derivatives are 2 hydroxyl, and that is for UV up to its UV 9 it is called 2 hydroxyl 4 methoxybenzophenone. So, which is also known as UV 9. Molar extinction efficiency is between 12,000 to 15,000. Now, next one is benzotriazoles. So, heterocyclic compounds offering broad spectrum within 290 to 380 nanometer. So, it is a UVB range which undergoes reversible photoisomerization. Reversible photoisomerization takes place. It is widely used, exceptional photostability with minimal yellowing tendency. And next one is commonly used is cinamates, which is conjugated ester. This conjugated ester derivatives, which is targeting the UVB 290 to 320 with that range. So, its main problem is with the limited photostability, and we can enhance this stability by stabilizer. Okay. And another is the salicylate. So, weak UV absorber. So, with the range of 290 to 315, with that range, with good compatibility with synthetic fibers, and it is actually often combined with strong absorbers for comprehensive coverage. So, these are the different ranges for organic absorbers. So, if we combinely used this depending on the range of UV absorption, that frequency range, so wavelength range if we want. So, accordingly we can use these absorbers depending on our requirements. Now, UV protection, the inorganic UV absorbers or UV protection chemicals, mainly metal oxides are used like titanium dioxide, which is commonly used for UV absorber as a UV absorber. So, different rutile and anatase crystal forms provided exceptional UV reflection and scattering. So, this inorganic UV protective chemicals like titanium dioxide. So, these are used for basically UV reflection and scattering. UV gets reflected. So, the band gap energy is, you can see 3 to 3.2 electron volt, enables absorption below 410 nanometer. So, it can get absorbed due to this band energy. So, nanoparticle size is 20 to 50 nanometer, prevent visible light scattering, maintains fabrics aesthetics. So, due to its very small size, so light scattering is not there. So, fabrics aesthetic color does not change. And the surface modification capability, the silica and alumina coating suppress the photocatalytic activity, preventing the fabric degradation. Okay. So, that with that this TiO2, when we are using that silica or alumina coating which suppress the photocatalytic activity. So, that we can use here, which prevents the fabric degradation, and refractive index here is 2.7, which optimizes the UV scattering efficiency. Next is the metal oxide is zinc oxide, which is commonly used, and where its energy, that band gap is here with the energy is 3.37 electron volt, which absorbs with the UVA and UVB ranges. So, within that range it can absorb. Lower refractive index, so 2 lower than titanium dioxide, and it has got very good biocompatibility. So, tetrapod nanostructure of the zinc oxide, enhance the surface area and UV attenuation. So, it has got special nanostructure, tetrapod structure, which enhance the surface area, and thus the UV attenuation is increased. Now, you can see here the UV blocking efficiency at 4 nanometer 40 nanometer particle size. So, you can see that with 40 nanometer particle size, it is 50 plus, okay, which is very good, and typical UPF rating achieved with 2 to 4% loading on the weight of fabric. So, 2 to 4% if we apply on the weight of fabric, we can achieve 50 plus UPF, the excellent grade, by applying the zinc oxide nanoparticle or titanium dioxide nanoparticle. Now, we will discuss different advanced technologies for UV protection. So, first is nanoparticle sol gel coating. So, UV absorbers incorporate in situ for uniform distribution. So, that in situ we actually incorporate UV absorber, and then this through the sol gel coating, and after that the curing takes place at 140 to 160 degrees Celsius, and to create covalent siloxane bonds with hydroxyl group on cellulosic materials. So, this in the sol gel coating we can use for any cellulosic group, hydroxyl group like cotton we can use. And next technology is that plasma enhanced chemical vapor deposition like CVD. So, chemical vapor deposition at a low pressure plasma, that plasma polymerization deposit an ultra thin UV blocker layers. So, the thickness is typically less than 100 nanometer. So, through the plasma low pressure plasma, the chemical vapor is deposited on the textile substrate and which acts as UV blocker. So, one is nanoparticle sol gel coating, next is the plasma enhanced chemical vapor deposition, and then third one is nano encapsulation system. So, where we create core sheath structure. Okay. So, core sheath architecture which encapsulate the core portion with UV blocking particle. So, inorganic UV absorber is there at the core, and in the sheath the polymer matrices, okay, which is typically melamine, formaldehyde. Okay. So, this is the sheath and core is the UV absorbers. the capsule diameter, total diameter of the capsule 1 to 10 micron, and the particle is in nanoscale. And here the core, presence of core controls the release. It is actually controlled release mechanism ensures protection. So, here the nanoparticles are there, that it actually release mechanism is controlled and prolonged protection through mechanical abrasion and laundering. So, here the whatever mechanical abrasion is there, that will be absorbed by the polymer matrix, but the actual UV absorber is encapsulated. And another technique is spray and padding method. So, conventional exhaust, that is liquid ratio 1:10 to 1:20 for batch processing, exhaust that batch process, and continuous padding with 2 dip, 2 nip. So, 80 to 90% pickup is followed by thermofixation. This are done conventionally, like padding method. Another method is the spray application, enables targeted deposition with minimal chemical waste. So, here the conventional exhaust process, that is batch process, we can use, or continuous padding method also we can use. There the chemical requirement will be high, because throughout the total area of fabric the chemical is added uniformly. But if we want to use in a targeted area, there we can use the spray application, which will actually minimize the chemical usage. Now, how to increase the durability of the UV finish? So, durability can be enhanced by cross linking. So, DMDHU and glyoxal resin, that forms the covalent bridge between the cellulose hydroxyl and UV absorber. So, that cross linking agent, so UV absorbers, between UV absorbers and cellulose, so that cross linking, so this is the cellulose and here is the UV absorber, and between that some resin like DMDHU, this type of resin we can use, that forms the covalent bond between these. And here we can use the catalyst magnesium chloride. So, 3 to 5% we can use to enhance the covalent the bridge formation, and after that the curing is done to fix the this bondage, the bridge. So, 150 to 170 degree Celsius we use for 2 to 3 hours, that is cross linking is done. And another method we can use to enhance the durability is silicon matrices. So, amino functional siloxane that which provides the hydrophobic anchoring agent. It provides hydrophobic anchoring, and that actually UV absorbers dissolve in the silicon phase. It maintains protection through 50 plus at home laundering as per ISO 6330. So, this maintains after up to 50 home laundering, more than 50 home laundering, it maintains the protection. And next one is resin encapsulation. So, acrylic and polyurethane binders are used which entrap the UV particles. So, UV absorbing particles, and film formation creates the mechanical barrier, and it is compatible with cotton, polyester and blends. So, this type of resin encapsulation we can do to enhance the durability. And after all this engineering, durability engineering, we can test the durability by AATCC 124 method. Minimum 80% UPF retention is there after 25 laundry cycle is required for commercial application. So, at least 80% UPF retention should be there, and photostabilizer prevent the absorbent from photolysis during outdoor application. So, that photo stabilizers are used. Now, let us discuss the multifunctional finish integration. So, not only the UV protection we have to incorporate. So, we cannot incorporate the finishing repeated time for same finishing application in one go. We can have multifunctional activities. Along with the UV protection, we can enhance other characteristics. Let us see what are these multifunctional activities. So, if we want to incorporate hydrophobic behavior in UV along with the UV absorber, so in that case fluorocarbon or silicon we can use that. These are the water repellent and combined with UV absorber. So, we want to create a fabric which is hydrophobic in nature, but at the same time it should be UV protective. So, in those cases we can use the multiple component. Here we use actually we apply in sequential manner. So, silicon is water repellent, we can apply separately then, and we then in sequential manner along with the UV absorber. So, sequential application prevents interference. So, because the application type there its requirement like the solvent requirement or temperature requirements will be different. So, that is why we use sequential application. So, oil repellency by ATCC 118 grade 5 to 6 is achieved with UV protection is maintained. So, that by sequential application we can do. If we want flame retardancy along with the UV protection, so for phosphorus based flame retardants are used which are compatible with the UV finish. Or titanium dioxide nanoparticles enhance the char formation, and dual functionality reduces the processing steps and chemical loading. So, if we use titanium dioxide, the titanium dioxide is good UV absorbers, and at the same time it forms the char on the surface which enhance the thermal protection, flame protection. It does not get the flame due to the char formation. So, that is why we can use this titanium dioxide for dual functionality. So, if we use the dual functionality, then that means the processing steps are reduced and chemical loading. Here we are using only single chemical. So, we must identify this type of chemicals which are dual functional. So, antimicrobial integration along with the UV protection. So, silver nanoparticles are very good microbial characteristics, and it is this type of compounds are applied along with the UV blocker. And here if you see, if we use zinc oxide, ZNO provides inherent antimicrobial characteristics, and at the same time ZNO provides the UV blocker, it acts. So, if we apply ZNO, so it can have dual functionality. So, critical for active wear and medical textiles. So, ZNO can be used. Self cleaning coating, so like lotus effect via hierarchical nano roughness. So, that we can use by silicon oxide dioxide and or zinc oxide, and where we can achieve the contact angle more than 150 degree. So, it is a super hydrophobicity we can achieve, and self dirt cleaning. So, dirt removal is there. So, self cleaning is achieved by zinc oxide, nanoparticle, and here we can also achieve the UV protection through the this nanoparticles. Titanium dioxide, okay, it is a photocatalyst, degrades the organic contaminants, and UV protection plus maintain the maintenance it is a reduction. Okay. Now, we will discuss the smart and responsive UV technologies. One is photochromatic system. So, it changes the color depending on the application, the presence of light. So, some chemicals undergo reversible molecular rearrangement under UV exposure. So, when the UV is exposed on a material, some chemical. So, color transition takes place. So, colorless to colored, it becomes an application, adaptive sunglasses and fashion textiles. So, when it becomes when we are going into dark into light, it become colored, and when we come to the dark or shadow, it becomes colorless. So, for sunglass application or fashion textiles, so as the color changes, so it enhances the UV protection capacity. So, this type of photochromatic systems can be used for UV technologies. So, this micro encapsulated photochromatic material can ensure the wash stability and switch speed. That means switch speed means that how fast it changes color. So, less than 30 second, that is the switch speed. So, within less than 30 second it changes the color and provides required protection. This is a responsive one, and thermochromatic indicator. So, we can have what is the temperature, how the temperature is changing by absorbing the UV radiation. Leucodyes like crystal violet lactones, this complexed with the weak acid display color changes as threshold temperature between 31 to 43 degree Celsius. So, UV absorbers integrated with the within the micro encapsulation core provides a dual functionality, UV protection and thermal warming. So, if you can incorporate this type of dye along with the UV blocker, UV absorber, so that will give the UV protection as well as the temperature changes. So, thermal warming it will give. Now, there are sustainable UV protection strategies are there. So, from we can get the UV protective chemicals from botanical extract, which contains the flavonoids and tannins, mainly from say green tea, pomegranate, aloe vera, which exhibits the UV absorption within the range of 280 to 320 nanometer, at that range. So, through the bio extraction we can achieve. So, main challenge here, they are not photostable. So, the photostability enhancement is required. So, we can use some photostability material which will enhance the photostability. We can use bio based polymers which enhance the, which will act as UV absorbers, like chitosan is there, and alginate biopolymers serve as UV absorbers, and renewable feedstock reduce environmental impact. So, that is important. There it will have, although it is a bio based polymer, but it will have environmental impact. If we it will reduce the renewable feedstock, and there are regulatory compliances, REACH compliant UV absorber mandatory in European Union. We have to follow this compliance. Okotex standard 100 categorize the requirement of toxicological testing. Okay. Zinc oxide is preferred over nano titanium dioxide because of the toxicological effect here, toxicological effect here. The future directions are the integration of AI driven formulation optimization. So, that will give us the prediction what type of this UV protection is required, bio inspired hierarchical structure, closed loop recycling of UV treated textiles. So, there should be reused and recycled, okay, and with next generation protective finish technology. So, these are the future direction. So, performance metrics must be balanced with the durability, sustainability and also obviously economic viability. So, it should not be very expensive. So, smart and advanced UV protective textiles are new generation UV protection materials that combine UV defense with intelligent sensing. So, this will sense the UV effect, UV protective effect, and it will adaptive response should be there, and also multifunctional performance capability. These are the different approaches for advanced UV protection. So, the smart textile foundations are, what is smart textiles? The smart textile integrate electronic component, sensor or responsive material directly into the fabric. So, which will respond, okay, which will sense. These advanced materials can detect environmental stimuli, whether there is a temperature change, what is the humidity, what is the level of UV, that all this information it will gather, and the information will be processed and respond dynamically to change the UV exposure condition. So, that in the textile itself, all these environmental conditions will be recorded. So, convergence of material science. So, we have to come together, all this material science, nanotechnology, electronics, and obviously in textile science, that they should come together and actively monitor, adapt and protect against the ultraviolet radiation in real time. So, all these technologies should come together to develop a perfect UV protective textiles. The core technologies are here for smart textiles. So, we must integrate the conductive fiber within the textile material to get the response from the sensors. Embedded sensor technology should be there. Stimuli responsive polymers like heat stimuli or maybe some chemical stimuli, moisture stimuli sensors, responsive polymers can be used, which material scientists can help. Flexible electronic substrate, wireless data transmission. So, these are the different core technologies as we have mentioned here. So, UV detecting sensor systems are used. So, photodiode sensors, so that detects the presence of UV. So, photodiode, silicon based photodiodes embedded in textile matrices. So, this silicon based photodiode, when we integrate these diodes with the textile structure, it measures the intensity of the UV ray which is coming to the on the fabric surface within the range of 280 to 400 nanometer. So, this type of photodiodes are sensors are incorporated within the structure. So, organic photovoltaic detectors are used. So, flexible organic semiconductors which provides a lightweight, comfortable, and it detects the UV. Integrated circuit system. So, miniature electronic circuit which actually get the data and cumulative UV doses it calculate, and then it triggers the protective response or user alert. So, this integrated circuit will give the trigger or it will give alert that whether the user is actually under danger or not. So, color changing UV indicators are also used. Chromogenic response mechanisms are there. So, photochromatic dyes undergo reversible molecular structural change when we expose to the UV radiation. So, there are special dyes are there. So, photochromatic dye. So, when it is exposed to the different level of UV ray, so it changes its color. So, depending on the UV ray the radiation, the frequency, it shifts the absorption spectrum to produce the visible transition. So, that the UV ray is not visible. Depending on the type of photochromatic dye, it actually create the color sensation. So, we can incorporate by fiber dyeing, surface coating, so micro encapsulation, this type of chemicals we can use, this dye we can incorporate in the textile structure. And wearable electronics for real time UV monitoring is also important. So, wearable UV dosimeters are there which will monitor the UV in real time. So, compact device tracks the cumulative UV exposure. So, UV the electronics, wearable electronics compact device which is incorporated on the textile material, which will be able to tell that how much UV exposure is there, and in the real time comparing the real time measurement against the daily safe exposure limit. So, that is that whether someone is actually crossing that safe exposure limit in a particular time, that it will give the signal, and it can be actually the algorithm can be framed for a particular skin type. So, personalized wearable UV dosimeters can be designed. So, textile integration systems are basically conductive yarns or printed electronic can give the this can provide this type of sensors. Connected mobile application. So, Bluetooth enabled data transmission allows the smartphone or to get the exposure history, and it provides the remedies. Okay. And if there is a the UV exposure, UV protection performance is reduced. So, then we can have reapplication remedies we can suggest, and it can also generates the health report. So, there are different methods of energy harvesting. So, flexible solar cell like photovoltaic fiber array, flexible solar cells convert the incident UV ray to visible light. So, and into the electrical energy, and which generates the power. So, energy harvesting we can get by proper application of UV material, and the flexible solar cell we can use the UV ray we are actually when we are getting, we can get the energy also, that visible light electrical energy we can get the generate the power, and piezoelectric generation we can do, and also energy storage integration we can make textile based super capacitor we can use, where we can use the store the energy. So, nanofiber membrane technologies are also used for UV protection. So, electrospun architectures are used. So, electrospinning produce ultra fine fibers, and which gives the exceptional surface area to volume ratio, and you can actually control the pore size, and with that we can block the UV rays. So, in nanofiber membrane we can achieve the UV UPF level more than 50, which is very good, and at the same time we can maintain the breathability and the flexibility is also. So, for multiple application we can use this electrospun architecture. UV absorber nanoparticles integration we can do. So, titanium dioxide, zinc oxide. Okay. So, different types of nanofibers we can use, and which enhance the breathability with better UV protection. Vapor moisture vapor transmission is very high, we can achieve, along with the UV protection more than 99.9% protection, almost 100% UV protection we can achieve by using the nanofiber membrane. So, ergonomic is always important for any protective textiles. So, understanding the science of human centric design in sun protective textiles is important. So, ergonomic represent the scientific discipline of design the clothing with optimize the human well-being along with the performance. So, in case of UV protective apparel, so physiological compatibility should be there, biochemical efficiency should be there, and sensory transmission should be there. So, it should be comfortable, and where the different fields, integration of different fields are important: human physiology, material science, cognitive psychology. So, that this type of science to be integrated. So, critical role of ergonomics in protective application. First and important is the enhanced compliance. So, if the fabric is breathable, it is ergonomically comfortable, then people will use and it will be properly. So, it minimizes the UV protection. So, that we should see the with the maximized UV protection, the human body movement should be perfect, performance optimization should be there, though ergonomic design should be such that the performance should be optimum. At the same time, health preservation, okay, properly designed garment will reduce the heat stress. So, the research demonstrate the discomfort is the primary factor of non-compliance with the protective clothing protocols. So, that is very important. So, the critical performance parameters are air permeability, thermal resistance, fabric weight, we have already discussed, heat stress prevention, along with that moisture vapor transmission. These are the critical parameters for any protective textiles, and we will stop here. In the next session, we will continue with the UV protective clothing, and there we will discuss some research studies and what are the effects on the UV protective textile, different textile parameters. Till then, thank you.